Okay, there it goes. Hey, good morning, good morning, good not morning, sorry, good evening, right? It's 5 o'clock. Grammatically, it should be good evening. You can say good afternoon also, okay? So, anyhow, so today we will discuss, interestingly, we have to discuss about two experiments, okay? Uh, we'll be discussing two experiments. I believe I am recording. Yes. And the reason for that is actually half of the class will be doing one experiment, other half will be doing the other experiment. So actually there are two experiments going on at the same time. As you may have noticed in the syllabus, it says here you can see on the screen for tomorrow, September 20, Group A will do steam distillation and Group B will do Soxhlet extraction. Followed by following week, you will switch. Okay? So the group that did steam distillation tomorrow will do Soxhlet extraction next week and vice versa. Speaking of which, there is something very interesting observation I have come across to see that later is this. So what happens is next week you do not have any lab. I think you know that there are no classes next week. Week of 26, no class. And guess what? Even the following week you do not have any lab because October 4th is also a holiday of something. I don't know exactly what it is, don't remember now, but there is something on October 4th for which we have no class. So there is going to look like the somewhat mismatch between lecture and lab. But what I will do, as I had written in the original announcement, I will try to synchronize a lecture just before the lab. That is going to benefit you the most. So, so no matter whether it's uh, that Monday is a holiday or not, if Tuesday is a lecture, a Tuesday you have a lab, I will give the lecture on Monday and it will be recorded. Those who can attend, you do. Those who cannot, that's also fine. For example, October 10th is a holiday. It's a Columbus Day. It's a Monday holiday. That means in theory I should not be lecturing, but actually I will only be, oh no, I will not. I tell you why. I will instead give you the lecture on Monday the 3rd. So I will give the lecture a week earlier because Monday 3rd I give lecture even though Tuesday there is no lab. Lab is going to be on 11th, the following week. Only thing is will look like skipped is this next week. No, next week is no class, so next week is just fine. So October 3rd, I will give you a lecture on Monday, but 4th, no lab. 10th, no class, I will give lecture because 11th, you have a lab. So I will do such swap. Or did I say incorrectly? No, maybe I will write it correctly in the in the announcement. So I'll give the lecture on October 3rd for the lab on 11th. Yeah, I think I have to correct myself. I confused you. So I'll write it down in the announcement. All right. So in other words, after today's lecture, next lecture will be on October 3rd. Next lab will be on October 11th. Okay. This time I said it correctly. So that's that. So that was the slight adjustment about the lab situation. So tomorrow, as I said, you are going to be doing two labs. So I need to quickly cover two experiments, which is not going to be a problem because one of them will require a lot of discussion or writing, the other one will not. So let me first with the one which is steam distillation. Oops, my screen is not responding very nicely as it normally does. Let me see what happened. Okay. So we will discuss about steam distillation. steam distillation first, followed by, I'll talk about number 2 is going to be Soxhlet extraction. So XHLET, Soxhlet extraction. Here is one thing, both experiments are going to have one objective, is to extract cinnamaldehyde. Okay, so objective is to extract cinnamaldehyde, and in general purpose wise, this can be utilized to extract any natural product, okay, from any natural sources. It can also be used to separate compounds, but separation is not usually the prime goal. Prime goal is usually to extract a natural product from other natural sources. So for example, but it also, as you do the extraction, it also causes the purification. Okay, so it will do the purification at the same time. So let me write it here, used for extraction and purification. How about that? Both extraction and purification of organic compounds, especially natural products. Natural products means natural organic compounds, natural products. So the model molecule for these two labs, even the following two labs, it is a kind of a sequence of 4 labs. Okay, keep that in mind. So both of these labs, first 2 is going to extract a compound called cinnamaldehyde. Third week will synthesize cinnamaldehyde from an alcohol, and fourth week you will do a lot of analysis using GCMS, NMR, IR, all those things. And that is the reason in the next lecture, since the theory of these both of them going to be discussed today, I will probably talk about GCMS briefly, and I can remind what you will be doing. That's going to be about it. That will be a short lecture, which will be in October 3rd. So there's that. So as I said, your model molecule for this is going to be the compound called cinnamaldehyde. Cinnamaldehyde is a molecule. It's a natural product that is found in cinnamon. Okay? Cinnamaldehyde molecule has this benzene ring and this carbon-carbon double bond, and there is a carbonyl group, CHO, if I write it this way. You may also notice the 2 carbons in the double bond, they are actually trans, or the double bond is a trans. So this is a trans cinnamaldehyde. So let me write it here. It is trans cinnamaldehyde. So this is the compound you are going to be working with for 4 weeks. So make a good friendship with this guy. Do some research online, whether it's Wikipedia or some other things. Try to learn more about it. One good reason is it is also the compound that is present in cinnamon. That is why cinnamon flavored dessert or muffin tastes so good, because of its flavor and sweet taste as well. But as you can see, the molecule is a large molecule. By that I mean, if you notice, its molecular weight is 132.3 grams per mole, which is not abnormally high, but it is high. More interestingly, its boiling point is pretty high. Boiling point is 248 degrees Celsius. That is obviously considered high, right? That is pretty high boiling point. You have not dealt with such high boiling liquid before. So when a liquid's boiling point is very high, it has to be treated or extracted by special means. For example, if you heat it up, then you have to hit extremely hard. That's difficult, and at the same time it can undergo thermal degradation. It can break down. Many things can happen. That's why we are going to be using two techniques that are very advanced techniques. You have not learned these techniques before. Organic One Lab, you have learned the basic techniques, although useful and important. Now we are going to be learning two advanced techniques. As a matter of fact, these two are the two advanced techniques you are going to be learning. So try to learn well and pay attention to the theory that I will talk about today. So let me cover a little more about this molecule, what you extract from, since we have been talking about, oops, this is a app of drawing up. Since you're talking about the extraction of this guy, so what are you extracting from? You are, as I said, you normally do from natural sources. You are going to be extracting from cinnamon stick, in fact, because cinnamon stick, let me write it here, cinnamon stick has about, depending on its source, it can be 2 to 4% cinnamaldehyde in it. Cinnamaldehyde. Even a poor grade can have 1%. So let's say between 2 and 4% would be a good approximation. So that's not much, right? That's very little. So which also means you are not going to be retrieving or extracting a tons of cinnamaldehyde from this. It is going to be small, but still it has strong flavor. So that's a good thing. Now, so first, as I said, we are going to be speaking of these two techniques and the principle behind that, steam distillation and Soxhlet extraction. So first we begin with steam distillation. What is steam distillation? As the name suggests, you can kind of guess you are going to be some kind of distillation with the help of steam. What is steam? Steam is water vapor. So, and another interesting connection is water has a boiling point 100 degrees, not extremely high, whereas this molecule has an extremely high boiling point 248. So we're going to use water to lower the boiling point, kind of. Not lowering, actually, you cannot really lower the boiling point. There, in principle, there is elevation of boiling point from colligative property. But we are going to see how it actually works, very interesting manner. So let me first ask you to get to boil something, you need to know its boiling point, roughly speaking. As I said, boiling point, I made the mention. What is boiling point? Do you know the definition of boiling point? How would you define boiling point? Anyone can say quickly? Although quick saying very quickly would be problematic. Okay, here Danny gave a brilliant answer. Thank you, Danny. That is the correct thing. When the vapor pressure of a liquid equals, she said, atmospheric pressure. So let me even refine Danny's definition. Atmospheric pressure is a general discussion, general understanding, and an approximation. More accurate statement would be when it equals the ambient pressure. But I'm going to explain. So, but you can actually write it down if you please. So, boiling point. Do not say when it's boiled. That is a third grade answer. That is a D level answer. So, boiling point is the temperature. First of all, it is a temperature at which the vapor pressure of a liquid equals the ambient pressure or its ambient pressure. Okay, because generally we assume atmospheric pressure is the atmosphere we live in. That is why it is usually expressed, but that's not scientific enough, because you can actually boil something at a pressure much lower or much higher than atmospheric pressure. There is going to be mind-boggling thinking that you think about it. So let me first indicate what we mean by this definition, even if we say that it is atmospheric pressure, and then I will give you the complete understanding. So as you see, there is vapor pressure involved. Now, vapor pressure, you know the definition of vapor pressure, perhaps vapor pressure of a liquid, which is the pressure exerted on the surface, right, by the liquid on the surface. Now, the vapor pressure of a liquid rises with temperature. Okay? Vapor pressure rises with temperature. So let me draw a diagram to make this point. So let's say here is a diagram to show. I'm writing on this axis vapor pressure, and let's use a unit of, let's say, torr, right? You are familiar with. And on the right, on the what is x-axis, we have put temperature. Temperature in degrees Celsius, right? Going up this way. So vapor pressure is the axis on the y-axis. So vapor pressure rises with temperature. So when you boil water, for example, water vapor pressure keeps rising. If I draw it like this, the vapor pressure keeps rising. So let me show you the diagram like this. Here vapor pressure very low at a low temperature, and then slowly it rises, just like a graph like this. So there is a slight curvature on this. So this goes like this. Okay? I may not have drawn exactly perfectly, but you understand that. It should be more perfect curvature. So what happens is, as the vapor pressure keeps rising up and up with increasing temperature, it reaches a point when that vapor pressure, as it keeps rising, becomes equal to the, as you said, atmospheric pressure. I was saying ambient pressure. Let's for the moment call it atmospheric pressure. 1 atmosphere equals 760 torr or millimeter of mercury. That we know to be the atmospheric pressure. And when we say water has a boiling point of 100, what we practically mean is that at 100 degree Celsius temperature, which is here, this number would be 100 degrees, then its vapor pressure becomes equal to 1 atmosphere pressure, and thus it boils, right? That's when it boils. Now, when we are talking about cinnamaldehyde, this is for water. Let me just write underneath, this is water. Now, if you compare this with, let's say, cinnamaldehyde, whose boiling point is 248, meaning only at 248 degrees, the atmospheric pressure or its vapor pressure will be equal to atmospheric pressure, which would mean its graph is going to be like, now I'm going to make a inaccurate diagram just to make the point. Let's say this is your 248 degrees, right? Your scaling wise doesn't make sense, right? It looks like only double, but it doesn't matter, right? You understand what I'm trying to mean, which means at that temperature, the vapor pressure will be equal. That means your curve is going to be much more flat. It is going to be just, let's see if I can draw correctly. So it will start like this. Maybe I use dot will be easier for me to show better. Now it looks better. So at this rate, it is rising. Maybe even it is more flat underneath. Let me make it more flat, more appropriate. Okay, that's okay. So that is for cinnamaldehyde. Cinnamaldehyde. So as you see, its vapor pressure is low, very low at low temperature. Even at 100 degrees Celsius, vapor pressure is very low, right? So it is not going to boil. To boil, you need 248 degrees. Then vapor pressure will be high enough to become equal to outside pressure. Now, when I was telling you why saying atmospheric pressure is not correct is this. Imagine, even if you consider this diagram, you can actually make water to boil at a temperature much lower than 100 degrees. How? Imagine if outside pressure is only this, then corresponding boiling point is going to be here. That is going to be 50 degrees. So you can actually make water to boil at 50 degrees if the outside pressure is this much, which would be roughly say how many, like maybe 300 degrees, right? 300, 400 approximately, right? That's only 300. So if your outside pressure is 300, then water will boil at 50 degrees. No wonder the boiling point of water is actually close to 95 degrees in Denver. 95 or 96, because in Denver the atmospheric pressure is not 760, it is much lower than that because of its higher elevation. Likewise, I should not say likewise, similarly you can say if the outside pressure is much higher, then boiling point will be much higher also, and that is indeed the case in a pressure cooker. You may have noticed that in your kitchen, your mom or grandma uses pressure cooker time to time to cook something that is very tough meat or other similar thing, or something to cook extremely rapidly. What happens in the pressure cooker? Have you ever pondered about that? Now you should. What happens is in pressure cooker it is covered, you probably noticed that it makes sound, etc. So it is closed system, pressure keeps rising, meaning your pressure is no longer 760, ambient is closed, therefore pressure keeps rising and rising. It can become almost 2 atmosphere pressure, or at least 1000 torr, or 1200, 1500 torr. That means if pressure is very high, now my scale is going out of the scale if it is here, do you see corresponding temperature is going to have to be much higher, because the scale is going to have to go this way like here. So temperature is going to be much higher. That is a much higher temperature, right? So that means in your pressure cooker, the water is actually boiling at a temperature much higher than 100 degrees, maybe 180 or 170 degrees. That is the reason everything cooks rapidly. Temperature is much higher in the pressure cooker. Okay, in the pressure cooker, temperature is much higher. So you can make water to boil at a very high temperature or at a very low temperature, depending on what the outside pressure is, where it is boiling. If you make the outside pressure very low, then you can boil at a low temperature. And that is actually a method used. We used to have an experiment in the past. We have stopped doing, discontinued that because our machine did not work very well. The reduced pressure, also called vacuum distillation. You create outside being vacuum, meaning low pressure. It was like 5 torr or 10 torr. See, if the outside pressure is 10 torr, then it is going to boil at a very low temperature. And that can be used to actually distill cinnamaldehyde, which we used to do. Because outside is very low, then let's say here is 10 torr. At 10 torr, you do not need such high temperature. That is going to require only 70 degrees or something like this to make it boil. Imagine like somewhere in here. That would be a situation where you can make cinnamaldehyde to boil at 70 degrees. So that would be reduced pressure distillation or vacuum distillation. This would correspond to what is called vacuum distillation. Although it is not exactly vacuum, but term is used in that way. But more grammatically correct would be low pressure distillation. Now, that is the discussion I'm giving just to just to enhance your general sense or common sense regarding this boiling and pressure situation. Now, let's come to our situation, the real practical experiment you will be doing with cinnamaldehyde. So, cinnamaldehyde is a liquid, boiling point very high, 248. You are going to distill it with the help of water. How? And for which, let me also begin to show a mathematical equation, and then I will come back to this diagram one more time. So let me write the theory, then it will make even more sense. Uh, it comes from a number of different laws. There is Dalton's law, there is some other laws, so I'm not going to make mention of those because it basically comes as a combination of number of those. So let me say this way: for a pair of miscible liquids, meaning if you have two liquids, pair meaning two, right? You understand? Pair of miscible liquids. Miscible, you also understand, something that is soluble to each other. Such a pair, if you have two liquids, they are miscible with each other. For example, if you mix alcohol and water, ethanol, they dissolve each other. That will be a miscible pair. For similar situations, the total pressure, if you are to heat it up, vapor pressure will rise, and the total pressure, let me just say P total, it will be equal to the partial pressure of A of one of those, since you are saying a pair, times its mole fraction Na plus partial pressure of B under standard condition by superscript not indicates a standard condition, and times the mole fraction of B, okay, where Pa, Pb are partial pressures and Na, Nb are mole fraction. I think that's practically you understand by now, right? P equals partial pressure, especially A or B, and N is mole fraction. Now, cinnamaldehyde is a large molecule. It is not soluble in water. So that is not going to be the case for this equation is not valid for that. Our equation is going to be valid for the slightly different equation I'm writing now. For a pair of immiscible liquids, now when they are immiscible, they don't dissolve each other. Here, just think for a second. That means the molecules are not mixing each other, oil and water type of situation. Their vapor pressure is independent of the other. Whereas a miscible pair, there is a dependence, and dependence somehow is equated into the mole fraction. But when they are immiscible, then their vapor pressure is independent of each other. When their vapor pressure is independent of each other, we can write P total would be just vapor pressure of Pa plus vapor pressure of Pb. You do not need to include partial mole fractions, which in our case, basically we are referring the partial pressure of water plus partial pressure of cinnamaldehyde. I'm writing Cin to indicate cinnamaldehyde. And this is the situation you are going to be dealing with. So we can write the total pressure is going to be equal to partial pressure of water and partial pressure of cinnamaldehyde. Okay, so when that is the case, let me take you to the graph for a moment, and I'll bring you to back to the equation. So what happens is, since you can just add up their individual vapor pressure to create the total pressure, what it means is that when you boil water and cinnamaldehyde together, because they are immiscible pair, you can just add up their partial pressures, meaning you can achieve this 760 torr pressure by adding the pressure of the two. So for example, if you were to add the partial pressure of let's say cinnamaldehyde, and you add with that the partial pressure of water, do you see two together become 760 now, right? So this is referring to let's say which color I use. This is partial pressure of cinnamaldehyde, and this corresponds to partial pressure of water. And guess what? These two together is becoming equal to 760. Since they are equal to 760, means they can now boil together. Okay? So it is like co-boiling. They are boiling together. So cinnamaldehyde as such will not boil at this temperature. Look at the temperature. Temperature is about 90 degrees, right? 90 or 95, don't need to be exact. Let's say it is approximately 95 degrees. So even at 95 degrees or 90 degrees, whatever that is, you are actually boiling up cinnamaldehyde, because even the small vapor pressure of cinnamaldehyde is adding up with the larger vapor pressure of water, two together is becoming equal to 760. See how interesting that is? Now you are becoming, running out of color, here your P cinnamaldehyde plus P water together is now becoming 760, which is the atmospheric pressure we mentioned. Now they can boil, right? So this is the clever technique that is being used, that you are able to boil up cinnamaldehyde even though it is high boiling, its own pure substance boiling point to 48. You are able to boil it up even less than 100, about 95 degrees, because its vapor pressure and water vapor pressure together is going to make a total pressure 760, becomes equal to atmospheric pressure, and thus they boil together. It is like co-distilling. All right. So that is how our whole technique is based on. You are adding up the vapor pressure of the two to get the total pressure. And that is only possible because they are immiscible with each other, which also creates a condition requirement in order to distill up a high boiling liquid in a steam distillation. The liquid has to be something that is not miscible with water. And then this would be true. Now, this we can further derive or do some calculation, some derivative of this. We can write in this manner, which would be this. The moles in this mixture, when they are distilling together, the moles of cinnamaldehyde, I think you will understand if I just write cin means cinnamaldehyde, divided by the moles of water will be equal to the partial pressure of cinnamaldehyde divided by partial pressure of water. Okay. Now moles that we wrote in the left side, moles is a unit of substance, right? The scientific unit. What is mole? Definition of mole, you know, mole equals gram over molecular weight or molecular mass, right? This equation you are familiar with. Mole equals gram versus molecular weight. Let's substitute this equation or the definition of moles, which is gram over molecular weight, into the equation I just wrote on the left side. Okay, we can rearrange. In fact, since you are advanced students, I am going to write the slightly rearranged thing. Gram of cinnamaldehyde divided by gram of water is going to be equal to partial pressure of cinnamaldehyde over partial pressure of water times molecular weight of cinnamaldehyde divided by the molecular weight of water. You can double check later that actually is correct from this definition of mole. Now let's further rearrange this to make more sense for us. Would be gram of cinnamaldehyde over gram of water. Let's say if I approximate that your this is an entirely crude approximation. Let's say an approximation. Let's say cinnamaldehyde is giving, let's say, about roughly 10 torr. Okay? It's not exact. I'm just making up a number for easy calculation. It could actually be 8 torr or 7 torr or 6.5 torr, etc. Which means if this is 10, then remaining part is 760 minus 10, right? Meaning it is going to be 750 water vapor pressure, steam vapor pressure. So that means we can write the partial pressure of water, partial pressure of cinnamaldehyde, which would be 10 torr, this is as an example only, and partial pressure of water would be 760 minus 10 would be 750 torr, times molecular weight of cinnamaldehyde. I just wrote 132.2 grams per mole, divided by molecular weight of water is 18. You know this. So of course units are going to cancel out, right? What does it turn that into? That turns into grams of cinnamaldehyde. I'm going to write in a more elaborate way. Grams of water equals, if you do this calculation, it comes out about 0.10 approximately. What it also means, here is the interesting part, what it also means, the gram of cinnamaldehyde is going to be equal, oh, this is water, is going to be equal to 0.1 times the gram of water. Water meaning water vapor in this case, right? You see this simple mathematical derivation? So what it means, it becomes 1.0 times. Now grams of water is up to you, up to us, depends on how much vapor we create. It depends on how much time you offer. You can use a conservative estimate. Even if you boil enough water to boil up 20 gram of steam, if we have this, remember this 20 gram is basically steam, meaning not liquid water. We are talking about the vapor, steam. This is steam. Water vapor is called steam. Okay, and this is only an example. It can be more, it can be less. If that is correct, then that becomes equal to 2 grams of cinnamaldehyde. Not bad, right? Not bad. You are able to extract 2 grams of cinnamaldehyde by way of co-distilling with water. And you had to spend only 20 grams of water. 20 grams of water being vaporized. Not a big deal. Again, by the way, this is an approximation only, and this is an exaggerated version. You will probably, this number I had said 10 torr for cinnamaldehyde, it is going to be a little less than that, meaning you are going to need more than 20 grams, but this helps you to work out the problem. And you can work out your problem using this calculation style. Okay. So this is what you are going to be actually doing. With the help of water vapor, steam, you will be collecting both liquid water and cinnamaldehyde together as you distill them off together. So distillation wise, if you imagine steam distillation, imagine something like this. It shows a 3-arm round bottom flask. It can be only 2 arms. On the side it is showing water, meaning you can add water if you need to. In your case, you will not need, and you have cinnamaldehyde or cinnamon stick actually is probably dipped in water for the whole week for you. The CLT did that for you. So you are going to get a kind of semi immersed thing together. It is still in the stick. Some of them will dissolve out, and as you vaporize it, heat it up, both of them together will come up. Uh, so it requires a larger sidearm only because it can sometimes cause some frothing. Make sure you put some boiling chips so that that doesn't happen. You may have to put slightly more boiling chips than you normally do because this is not a pure liquid. You have a high boiling thing, and cinnamon stick has some other cellulose and other stuff, so you may want to put uh, significantly more boiling chips, not only 2 or 3, put 5, 6 of them. So the vapor that is coming out, that is a mixture of, let me use an approximation, 10 torr of cinnamaldehyde and 750 torr of water. That's coming as a vapor, but as you condense it, in the end you get liquid. So on the right hand side you are going to get liquid, but that liquid will have a small amount of cinnamaldehyde and a lot of water. They are immiscible. They will come as a pair of liquids immiscible with each other. Okay, and you are going to be using only most probably a test tube. You will not need to do this way. The test tube would probably be just fine. So then you have two immiscible liquids, so you can easily separate out the two liquids. Separation of two immiscible liquids is not a problem. You may not need to use a separatory funnel. You can just use a dropper that will do initial approximate separation. Okay. Here is one additional technique or trick, I should say, goes with it. When you have two liquids, you are collecting together, forcing them to come together. What happens is, even though in a test tube, they may not be separated into two separate liquids as nice layer as possible because they just work together in the gaseous state. Both are vapor. So even though the two of them are supposed to be there, okay, and there should be some amount of cinnamaldehyde and plenty of water, say like this, but the separation may not be very good. Okay, you may see some overlap, which is what is sometimes called forming an emulsion or not separating well. When the two immiscible liquids are not separating well because they were in a molecular state, you just condensed them, then there is going to be some, what is it called, small molecules of each can be dispersed into the other, which is what is called an emulsion. An example of that is your milk. Milk is an emulsion of fat particles and water. So you can see such thing, cloudiness. If you do see, there is a technique called salt out. You may have heard or used before. Salt out. Have you heard the word salt out? Have you heard or used before? Anyone? Yeah, very good. You heard it. So what is salt out? Do you know what that is? How to do that? Danny, that you answered? Oh, that's good. Then I need to talk about it, right? So that is used in a case like this when the two immiscible liquids are almost not separated well, forming an emulsion or emulsion like partially separated, not well separated. Then you use salt out. Then you do salt out. I should not say use, do salt out. How do you do salt out? You do that by add, I'll write two ways. Add saturated sodium chloride solution or solid or solid sodium chloride. Okay. Even adding solid sodium chloride also works. Ideally, using saturated sodium chloride is the correct process to do that, because adding solid crystals is kind of a messy, not a good idea. But sometimes that is also done by experts. Saturated sodium chloride. So what happens is, when you add saturated sodium chloride solution, the two liquids get separated. Okay. So when you are adding sodium chloride to that, whether it's saturated solution or solid, then these two will be well separated. Can you tell me why? Why it will help separate the two liquids? If not, that is okay. Just if you think something you can tell. If not, I tell you right now. What happens is, the reason two liquids are immiscible, that is the based on the principle you learned in organic 1, in fact, like dissolves like theory. So if they are unlike, then they don't dissolve, right? If they are like, they dissolve, meaning their polarity is same, they dissolve. If the polarity is different, polarities are different, they don't dissolve. But here the polarities are different, but still they are kind of somewhat mixing in an emulsion. So by adding sodium chloride, what you are actually doing, the polarity of aqueous layer is being increased, because sodium chloride is an ionic substance. When such strong ions go into water, water's polarity is greatly increased. There are several number of terms that is also can be used from physical chemistry, which is it actually its ionic strength increases, or dielectric constant increases. Those are heavy duty terms. So simplistically, to understand, even the very basic understanding the polarity difference between two liquids is the reason why they don't dissolve each other. If you can increase that difference in polarities, then they will separate. So by adding sodium chloride, you are actually increasing the difference in polarities between the two liquids. So if the water's polarity is increased, your cinnamaldehyde is not increasing, but the difference is increasing. When the difference is increasing, they separate out. So that is more abstract way of thinking or saying, and it is correct. Mathematically, that is correct statement. If you want to think slightly more chemically, imagine cinnamaldehyde, even though it is large molecule immiscible in water, as a matter of fact, it has a polar covalent bond. It has an aldehyde group. So it can actually make hydrogen bond with water, right? Aldehyde group is a polar covalent bond. So it would be able to make hydrogen bond with water, with oxygen. So if it makes hydrogen bond, then it can actually, some molecules can held onto that, even though it is not fully being dissolved. So there is going to be some water stays there, because there is some attraction. But by increasing the polarity of the aqueous layer, now we are increasing the gap between the two, increase the difference in polarities, making them having no choice than to separate out, leave each other alone. Okay, that is the reason they get separated. So that is the all the theory and principle of uh, steam distillation. I should include a few interesting things. The success of steam distillation depends on three factors. So factors, let me write this way. Factors for successful extraction by steam distillation. So as you can see, these are the things I'm explaining, and these are the things, exactly these things I will write, I'll put in questions in exams. So your exam is never a surprise. It's all about the things I taught here. I said that on the first day also. So what are the things that will help? First of all, as you understand, they have to be immiscible with each other. No? Right? So generally, we are having one higher boiling liquid, let me even write the higher boiling liquid, meaning the one we want to separate by steam distillation. They are always higher boiling. Higher boiling liquid must be immiscible with water, because that is where the theory applies, right? I just wrote the equation for that. Number two, the compound does not react with water. If they react, then that's a disaster, right? Number three, here is an important one. The vapor pressure of the compound, meaning that organic compound, must have some the compound must be let's say approximately 5 torr or more near the boiling point of water. That way, two together can combine, become 760. So if it is very small, then you are not going to get much. It will take forever. So it should have appreciable vapor pressure, something like 5 torr or so. Okay. Question. I'll see the upload later. Yeah, that's fine. That's fine, Anthony. Please take a look later. That's okay. I'll see you later. Anthony, you can leave. That's understandable. All right. So that's your three conditions that is necessary to have successful steam distillation. So now briefly in 10 minutes, I'll talk about Soxhlet extraction, because I need to tell quickly because some of you will be doing that tomorrow. Soxhlet extraction is done basically using a solvent that can preferentially dissolve one liquid over the other. Here, Soxhlet. And for which we can exactly use the like dissolves like principle more accurately. Basically, you want to have a solvent that is a perfect match for the compound you want to dissolve. Some of the most common organic solvents, there are many, you may have seen in Organic Lab 1, organic solvent that is most commonly used. One is, of course, diethyl ether. Right? Let me use different color. Oops. Diethyl ether is most common. You know this guy, diethyl ether. It is very convenient because it dissolves almost any organic compound, and its boiling point is very low, 34.6 degrees. So it is easy to get rid of. And another very good compound is T-butyl methyl ether, also written as TBME. It stands for tertiary butyl methyl ether. Its boiling point is slightly high, not all that great. You can also use dichloromethane, which is also a fantastic solvent. Its boiling point is close to 40 degrees, not too bad. Only problem is nowadays all chlorinated solvents are being avoided because they are suspect for any carcinogenic effect. Boiling point close to 40 degrees. So that is being used far less. So in your experiment that you will be doing, I'll show that very quickly. This is the setup. Setup is going to be, has to be shown by your TA, and it has a very interesting, unique characteristic. How can I show this? So what you are seeing at the bottom, you have a solvent, one of the ether or something that is going to be boiling, and as you see the color, which is the solvent, it boils, it goes up, all the way up. When it goes up, on the very top, there, can you see my cursor? On the very top, you have a condenser. It says water in, water out. The blue color showing water, cold water, or the condenser. And as you can see, the solvent, the orange color vapor goes up, and as it goes into the condenser, it condenses and becomes liquid and drops down. But it drops down in a very unusual device called a thistle funnel or a thimble, in which there is a specialized type of paper, semi-permeable paper. Inside that, it's a big pocket type of thing, kind of a not exactly hardboard, but special type of paper, thick paper. Inside that, you will have crushed cinnamon stick. So cinnamon stick initially crushed, basically making small, not necessarily powder. That is inside that, and it stays there permanently. That is set up correctly there, but it is inside this particular thimble apparatus. So when the solvent drops from the top, it dissolves your cinnamaldehyde from there. But there is cinnamaldehyde, as I showed, only about 2%, 2 to 3%, very small amount. So by dissolving, you don't get much. However, in this method, as the solvent comes in, it dissolves, and it continues because solvent is dropping from the top continuously, slowly filling up this thimble apparatus. And there is an interesting device on the side arm you see, which is that it has the arm, top of this side arm is slightly below the top of the thimble apparatus or thimble funnel. As a result, when enough liquid accumulates inside, of course it dissolves cinnamaldehyde a little bit, and it goes high enough that it slightly passes this side arm's upper point, then it drops down by siphon mechanism. This is called siphoning. Many of you have heard or learned before. This is siphon mechanism. So through siphon mechanism, this thimble apparatus, which is like a big funnel, that gets emptied out completely. You see here in the picture, as you see, it becomes, at one point, it becomes empty. It fills up, and siphon causes it to empty out. And as it empties out, this the vapor from the solvent never stops because you continuously heat. That goes up from the other larger side arm of this Soxhlet apparatus. Whole apparatus is called Soxhlet apparatus. So that is going on and on and on and on forever, which means the solvent is dripping from the top, pretty much warm solvent, continuously into this thimble funnel, and it is dissolving and siphoning down. Process keeps going and going and going. So each filling up and siphoning down, we can call it one cycle. So roughly in your lab, you are going to do about 8 to 10 cycles. More cycle you do, more extraction you get. Of course, 2-3 cycle will not do much, but if you do 8 to 10 cycles, then you are going to dissolving out a sufficient amount of cinnamaldehyde from the cinnamon stick into the solvent being accumulated in the round bottom flask at the bottom. So at the end of this 8 or 10 cycles, you can stop it, and then your goal is to get rid of the solvent. That is why you're using low boiling solvent such as diethyl ether or TBME or whichever. You can always remove the solvent by using rotavapor. I'm sure you have used rotavapor in Organic Lab 1. You will be using that again. That is a rotary evaporator. It slowly evaporates the solvent. In fact, because it rotates, it is pretty fast, not necessarily slow, leaving your compound behind. So this is another interesting way to extract a high boiling liquid without boiling. Here whole thing is being done at room temperature, and the temperature is only the temperature of this solvent, which is a low boiling solvent, only 35 degrees, right? So you are not hurting your cinnamaldehyde molecule, yet you are being able to extract it. Okay? So that is what is about extraction method by Soxhlet extraction. So here is Soxhlet apparatus. You have to use it very carefully, of course, in the hood, because it is also extremely expensive. Okay? So the last word I was using, the method by which it comes down is called siphon. Siphon, siphon mechanism. Uh, uh, Liquid comes down. Okay, so that is your Soxhlet extraction. There is no additional theory. Only theory is like dissolves like, and using appropriate solvent, you use many cycles, and by siphon mechanism it comes down. Finally, followed by you separate the solvent by rotavapor, and you get your compound behind. That's it. And in a third or fourth week, you are going to analyze whichever you are collecting tomorrow in your steam distillation as well as this. You will preserve it, don't throw away, which you are going to analyze in the fourth week. Third week, you will synthesize by chemical reaction. Fourth week, these two, and the third week synthesis product, all these are going to be analyzed in the fourth week. All right. So that's all about today's discussion, which also means next week you do not have lab. Following week, I will give you a short lecture on Monday, although your lab will be on 11th. But actually, the lecture material I have actually covered since we covered two theories today. It may be possible, I will check how I could possibly give you a midterm test on of those days. I am hoping to do that on a Tuesday 12:30. I am assuming that they will work for you. Tuesday 12:30 is probably free for you guys, such that I can do in person. Uh, you should not have class conflict. I will send you an email about this. All right. That's about it for today. If you have any questions, you can raise hand. Otherwise, have a good night. You're welcome. I'll stop recording. Okay, thank you, Anastasia. Stop sharing, stop recording.